In this video, we're going to state and prove a rather simple lemma of Euclid and a theorem of Euclid as well. So the first one, the lemma, says that if A divides the product BC and the greatest common divisor of A and B is 1, then A divides C. Now remember what this means, the greatest common divisor of A and B. That means A and B share no common factors other than 1. Okay, so if that's the case, that means that A must divide C. And here's how the proof goes. Since the greatest common divisor of A and B is 1, do you remember from the previous theorem, that means that whatever the greatest common denominator is, there's some linear combination of these two numbers A and B that will give me a 1. So let M and N be integers such that 1 is equal to AM plus BN. And I'm mentioning that it's possible by the previous theorem, the previous video. Okay, thus, I'm going to multiply the entire equation by C. Okay, the number C, and that would give me C equals C times AM plus BN in parentheses. And maybe I'll go ahead and distribute that. That implies that C is equal to C, or maybe I'll write it like AMC plus BNC. So I just distributed the C through both of those. All right, well, we're actually almost done. Since A divides AC, and I hope I don't need to explain that too much. All this says is there's an integer I can multiply A by to get AC, and it would be the integer C. So this should be trivial. And A divides BC, that's what we're given up here. A divides BC. We see if it divides both this and this, it'll divide any linear combination of AC and BC that we saw from that fact, number theory fact 6. So we have that A divides, in parentheses, AMC plus BNC. And I'll make a note by fact 6 from earlier. So all we did is we noted that A divides AC, A divides BC. So I'm going to multiply AC by M. I'm going to multiply BC by N. And I know that A divides that linear combination, AMC plus BNC. And to finish it off, therefore, let's see, I'll factor out the C here, and I'll get AM plus BN, like that. And then note that this is equal to 1. AM plus BN is equal to 1. So what we end up with is A divides C. Okay, so pretty simple lemma and pretty simple proof, and we will use, well, before we move on, let me just do a quick example of what's going on here. Let's say, example, 3 divides, excuse me, 10 times 18, which is 180. Right? Why does it do it? Because 3 times 60 would give me 180. All right, well, since the GCD of 3 and 10 is what? What's the greatest common divisor of 3 and 10? Well, clearly it's 1. Right? So what this lemma is telling us is that 3 must divide. If it doesn't, if the GCD of 3 and 10 is 1, they share no common factors other than 1, 3 must divide 18, which of course we know it does. So that basically just kind of, this example just demonstrates the lemma. Okay, let's move on to what we're calling Euclid's first theorem, or Euclid's principle. And it says that if P is a prime number and P divides A times B, then either P divides A or P divides B. So once again, P is prime. If it divides AB, it means P goes evenly into A, or it must go evenly into B. And for the proof, let's start off by saying that if P divides A, then we're done, obviously. Okay, so otherwise, we'll assume that P does not divide A. For the rest of the proof, we'll assume P does not divide A. Well, that means that P is a prime number. So, since 1 and P are P's only prime positive factors, since it's a prime number, we see that the greatest common divisor of A and P has to be 1. Correct? Because we know now P does not go evenly into A by this assumption. If P did, we were already done. Otherwise, remember, we said P does not divide A. And we know that A doesn't divide P because P is a prime number. So, by Euclid's lemma, which was above, just above, we see that P divides B. And we're done. So basically we showed it either divides A or it divides B. And there are a couple of corollaries I'll write down. They're really just one-liners. We'll say corollary 1. Maybe I'll call it corollary I. P prime, I'm going to abbreviate these a little bit. P prime and P divides these numbers A1 times A2 times AN, this product of all n of these numbers. That implies that P divides one of these AIs, A1 through AN. Because P is prime, if it divides this product of numbers, P must go evenly into one of these numbers. So P divides, I will call it AK, for some K in, what do we went one from 1 to N. So that just says that there is at least one K, where K goes from 1 to N. It could be 2, or N, or 1, or anything in between. P must divide one of these factors. All right, maybe I could do a quick example on that one. Notice that, let's see, 5, does 5 divide 1 times 2? No, 5 does not divide 2. Does it divide 3? I'm sorry, 1 times 2 times 3, which is 6. No, it doesn't. It does not divide 6. So let me put another one on. 1 times 2 times 3 times 4, which is 24. 5 does not divide 24. But if I take 24 and multiply it by 5, I get 120. Now, 5 divides 1 times 2 times 3 times 4 times 5. 5 is a prime number, which means 5 must divide one of these numbers. And finally, we got it. It's this one right here. That was a very simple case. That's just a very simple example. All right, let's look at corollary II. P prime and P divides some number a to the nth power implies, well, what do we think? In this case, the n copies of a, that means it's n copies of the same number. So if it divides a to the nth power, the p, the prime number, must simply divide a. And let's see if there's a simple example. Well, I could do 5 again. For example, 5 divides 125. Well, 125 is 5 to the third power. And that's 5 times 5 times 5. And 5 divides each individual 5. So again, another trivial example.